Thank you organizers for giving me this opportunity. Today I will speak on decoding quantum chaos through eigenstate correlations. This is a joint work with Rahul and Statistical. We all are from ICTS only. Um, so the kind of system I will speak for the next 8 to 10 minutes will be locally interacting quantum chaotic systems. By locally interacting, I mean the Hamiltonian of the full system. It can be written as a sum of local terms. For example, it can be some nearest neighbor interacting chain. The eigenstates of the unitary operator or the quasi-energies of the unitary operator, those are identified by this theta alpha and this alpha are the eigenstates. So, and by quantum chaotic system, I mean, we look into the correlation functions in space and time, and we look into what is the fate of these correlation functions and at long time. So, in chaotic system, we expect that at long time the operators will be statistically independent to each other. So in any quantum system, if you have all the eigenstates and all the eigenvalues, that is basically the joint distribution of eigenstates and eigenvalues. You can, in principle, write any dynamical quantity in terms of this joint distribution. But in quantum system, the dimension of the system increases exponentially with the length of the system. So the information encoded in the eigenstates and eigenvalues will be huge, and maybe that much information we don't need for a kind of dynamical quantity. So the questions that we ask are what are the minimal correlation that we need to explain this kind of dynamical quantities like local correlation functions or purity or the entanglement entropy, and what are the universal properties of the eigenstates in locally interacting quantum chaotic systems, which will separate it from non-local chaotic systems as well as from integrable systems. So let's go back to the literature and why we are interested in this question and what is the motivation. So the simplest and the crudest approximation that we can make for the eigenstates in a quantum system will be within some fixed energy window. They are just some Gaussian random vectors. That means once you specify some energy window, the eigenstates can be identified by some Gaussian distribution. Though this approximation may look like too simple, but it explains even though the dynamics in an isolated system is unitary, why it thermalizes locally. The one better approximation that we can make beyond this, that will be adding orthonormalization, that eigenstates are orthonormalized as well. Then we can explain not only two-point correlator, but also the higher point correlators. But the kind of dynamical quantities that we are interested in are cannot be explained through these two kind of approximations. So that is adding one more approximation to the already existing one. So these dynamical quantities are basically these k-point spatiotemporal correlations or the entanglement entropy or the dynamics of the purity. The common thing about the dynamical quantities that we are interested in are they are all sensitive to the system being locally interacting. So that's why we want to understand what is this, what are the imprints of local interactions in many-body eigenstates. And this question may sound tough because eigenstates in a chaotic systems are delocalized, they spread over the full Hilbert space. So having some local structure to these eigenstates may be very fine structure and all. So to identify this, we consider an approach that is basically we write down the eigenstates in some tensor product basis, where I can be thought of some tensor product basis in real space, and we split every eigenstate in this bipartite basis. So we write the eigenstates which was initially a vector. Now we write it as a matrix, where the two legs of the eigenstates are corresponding to the basis states in the subsystem A and the subsystem X bar. And we ask what kind of correlation that we can build from these eigenstates. The simplest correlation that we can build is just from two eigenstates, and that is just the orthonormalization condition. The next order non-trivial correlation that we can build is from four eigenstates, and that is basically taking four eigenstates and writing them in some matrix notation, and if we take trace accordingly, we can construct a scalar. Independently, these scalars are not gauge invariant, but we can make them gauge invariant by considering another eigenstate correlator, which is defined at some y. And we do not want to pick four random eigenstates from the spectrum, and so we specify some energy window in which we take these 4 eigenstates. So one can define this kind of eigenstate correlator in a quantum system, or also can look into their structure in the time domain. So in principle, I mean, in general, one can define one can define 4 kinds of this eigenstate correlation, but they are related due to the symmetry coming from the bipartition. So we understood that if we can consider this kind of eigenstate correlations, maybe we can identify the local structure. But how are they related to the spatiotemporal observables that I had shown in the earlier slides? So it turns out that the spatiotemporal observables that we are interested in, like the 2-point autocorrelation function, or the mod square of the 2-point autocorrelation function, or the higher point correlators, like 2-point correlation function, or the higher point correlation functions like the out of time order correlator, they are just different avatars of this or different forms of this eigenstate correlation. And also the entanglement entropy, that can also be, or the purity, which is related to the second Renai entropy, that can also be written in terms of this eigenstate correlations. And since we understood that this kind of dynamical quantities, be it local or the kind of quantity like entanglement entropy, can be written in terms of this eigenstate correlation, can we calculate them exactly, at least in some kind of dynamical system? So here we consider a specific kind of system. Those are known as dual unitary circuits. So in general, in any quantum system, in any chaotic system, we cannot calculate this kind of correlations exactly, but this kind of circuits has a special structure. That is, the full Floquet operator is basically a tensor product of this local building blocks or local gates, and these blocks actually satisfy the unitary condition. That is basically their identity when we multiply with its the dagger of this. We introduce another property of another structure into this building blocks, that is this dual unitary property. So they are not only unitary in time, they are also unitary in space. So once we import this condition that they are unitary in both space and time, we can calculate quantities like entanglement entropy, local autocorrelation, local correlators, or the out of time orders correlators exactly. So for entanglement entropy in this dual unitary circuits, one can calculate the light cone structure and how does it depend with time. That is actually it grows ballistically with time, and one can find out the structure of purity. From there, one can comment on this eigenstate correlations. And this eigenstate correlations has this specific structure that it has this sin omega over omega like structure, and as you can see, I can no longer separate the contributions from eigenstates and eigenvalues when I am explaining this kind of dynamical quantities. They are coupled here, I mean this product like omega and r. We can also try to explain quantities like 2-point correlators, and for those the kind of eigenstates correlators that are responsible for them are this. So basically it has the following structure, that it's some periodic cos wave and with some envelope which is decaying exponentially. For out of time order correlators in this dual unitary circuits, they are one outside the light cone, within the light cone they decay exponentially, and which implies that the eigenstate correlator will have this kind of structure, that is this sin omega over omega like structure. So by this way, by introducing the idea of locality into the structure of the eigenstates, we can explain the spatiotemporal observables, and when we explain the spatiotemporal observables, we cannot separate the joint function into the individual contribution from the eigenstates and the eigenvalues. We have to consider the joint function as a whole, and these are the future questions that we are looking into currently. Thank you for your attention.
Thank you, Bikram, for such a nice talk. Questions?
Okay, I'd like to know if you take h bar goes to 0 from your quantum chaotic system, you take the classical limit. What do you expect? Have you investigated that?
That we are not.
That will be chaotic, I know.
Yeah,
that has to be chaotic.
Yeah, but
I would like to know the gory detail of that. Have you investigated?
Okay, but the kind of
My second question is, from you, the insights you get here, if someone asks you to lay down the necessary and sufficient condition for quantum integrability, what would be your comment on that?
Okay. To answer your second question, I mean, this eigenstate this structure that we can write down the local correlation and entanglement of in terms of this eigenstate correlation, this is not specific to chaotic system. We can do it for integrable system as well. So basically for integrable systems, I mean, we had worked on integrable system as well. So basically the necessary and sufficient condition that are actually encoded in this correlators basically. And that has a different kind of structure compared to chaotic system.
But if it is integral, it should not be chaotic, right?
No, I'm saying the structure is just different from chaotic. Okay. So this spectral function that has different structure in the integrable case.
More related to the structure.
Yeah.
Inherent to quantum.
Yeah.
Quantum integrability.
Yes.
Okay, so let's thank the speaker. Oh, sorry. No, it's okay. Yeah.
Okay.
Yeah.
Quickly.
Yeah,
So this boundary of the entangled region, in some cases it has been shown that it has relation to the Fisher-KPP equation, and the velocities is given by the velocity selection. Do you find something similar through this exact characterization that you have in this system?
So you mean this this light cone like structure?
Speed of the region.
Yeah, that actually we can identify using this correlations. I mean, in this kind of circuits, we can exactly calculate, and these are actually these maximal velocity circuits, so they satisfy this bound.
But you don't see any relation to Fisher-KPP kind of equation?
No.
Not. Okay, thank you.
Okay, thank you.